Britain entered the Second World War with a secret weapon that, ironically, could not go where it was most needed. Along the windswept cliffs of the English coast, huge steel towers stood like industrial lighthouses, crowned with aerials the size of railway carriages. These were the chain-home radar stations, the world's first operational early warning network, capable of spotting Luftwaffe bombers at nearly 70 miles. RAF commanders watched grimly as the plots crawled across their screens, scrambling Spitfires and Hurricanes to meet the threat in daylight. Yet this scientific miracle carried a crippling flaw: it was bolted permanently to British soil. Once night fell, those same fighter pilots were left essentially blind, armed only with their own eyes and the sweeping glow of searchlights clawing at the sky below. The Hurricane cockpit barely spanned 4 feet across and housed only the most essential dials: altimeters, compasses, and fuel gauges. Nothing that could pierce the darkness ahead. RAF Tangmere's night fighter crews patrolled for hours above the dark Sussex countryside, listening to controllers on crackling radios attempting to talk them toward targets they almost never managed to see. And the Luftwaffe understood perfectly how blind Britain became after sunset. German bomber streams used that blindness ruthlessly, gliding in under the cover of darkness to strike docks, factories, and civilian neighborhoods. Fighter Command, helpless in the dark, managed fewer than 1 kill per 100 sorties. Britain was fighting half-blind, not because of lack of courage, but because physics itself was the enemy. Chain-home relied on meter-long wavelengths and mammoth aerials because detecting an aircraft at 10 miles required transmitters capable of spewing thousands of watts into the sky. Valves powerful enough to generate that energy weighed hundreds of pounds and emitted alarming amounts of heat. Even if engineers could somehow cram the equipment behind a pilot's seat, the meter-wave aerials would create so much drag the fighter could barely catch a bomber. Squadron leaders dismissed the idea entirely. A radar-equipped fighter slower than its prey was worse than useless. Still, the Air Ministry issued a specification for airborne interception, AI, as it became known, requesting a system that could fit into a Blenheim or Bow fighter, detect targets at several miles, and weigh less than 500 pounds. Physicists responded with pages of equations proposing shorter wavelengths that allowed smaller aerials, but the valves of 1939 could not generate meaningful energy at higher frequencies. Laboratory transmitters operating at half-meter wavelengths produced barely 10 watts, scarcely enough to light a torch bulb, much less reflect off a distant Heinkel. Engineers across the globe, German, French, American, agreed on one bitter truth: airborne radar required a breakthrough no one knew how to achieve. At high frequencies, electrons inside ordinary valves traveled distances comparable to the wavelength itself. Transit time effects ruined efficiency, and the valve stopped functioning as an amplifier. Every scientist who worked on radar knew this limit. It was, in their minds, immovable. But Britain was burning, and immovable laws had to give way. Into this crisis stepped John Randall and Harry Boot, two unlikely heroes in Birmingham University's physics department. Randall, a 34-year-old spectroscopist, studied how atoms absorbed light. Boot, 27, had spent his doctorate investigating how electrons behaved in magnetic fields. Neither man had designed radio valves. Neither was a radar expert. Their professor, Mark Oliphant, received a desperate question from the Air Ministry. Could British science possibly create a device that generated immense power at a wavelength of about 10 centimeters? Oliphant assigned the job to his two least experienced researchers because fresh minds often see paths experienced experts declare impossible. The magnetron already existed as a concept. American engineer Albert Hull had built a primitive version in 1921, where electrons spiraled through magnetic fields rather than moving in straight lines. But by the 1930s, magnetrons were scientific curiosities, weak, finicky, and utterly unsuited to military use. Randall and Boot dug through old journals, studying every failed attempt. They recognized the core challenge. Conventional valves wasted most of their electron energy as the electrons slammed into the anode. The question became, could you coax that electron cloud into resonating, forcing it into rhythmic oscillations at microwave frequencies? Boot sketched an audacious idea. Instead of a solid anode, imagine a copper cylinder drilled with 6 perfectly sized circular cavities. Each cavity would act like a microscopic echo chamber, resonating with electromagnetic energy at extremely high frequencies. If the cavities were precisely 1 centimeter across, they would naturally resonate at around 3000 megahertz, or a 10-centimeter wavelength. Place a heated cathode at the center, impose a powerful magnetic field, and electrons would spiral outward through the cavity openings, inducing microwave oscillations. The waves would reinforce the electron bunching, which would reinforce the waves, creating a self-sustaining cycle that converted raw electrical power into microwave energy with extraordinary efficiency. Randall calculated the expected output. If their math was correct, this cavity magnetron might generate a kilowatt of continuous power, a figure so absurd every experienced radar engineer would have laughed outright. Existing microwave valves barely managed 10 watts. 100-fold improvement seemed like fantasy. But equations, stubbornly, insisted it might work. They needed proof. In Birmingham's workshop, technician Mr. Skinner spent 3 painstaking weeks machining the prototype from solid copper. The cavities had to be positioned with 100th-inch accuracy or the entire device would fail. They scavenged a tungsten cathode from a broken radio valve and salvaged a permanent magnet from an old loudspeaker to generate a powerful magnetic field. Once the copper block was sealed inside a vacuum housing and wired to a high-voltage supply, the moment of truth arrived. On February 21, 1940, they switched it on. The magnetron immediately burst into oscillation. A neon lamp held near the output aerial glowed brilliantly, wirelessly, lit entirely by microwave radiation blasting from the cavities. Boot measured 400 watts continuous output at exactly 10 centimeters. Randall called Oliphant. Oliphant called the Air Ministry. Within 48 hours, Britain's top radar scientists were gathered around a battered laboratory bench staring at a copper block that had just changed the war. When Edward Bowen, Britain's leading airborne radar pioneer, arrived, he demanded a full test. The magnetron produced not 400 watts, but over a kilowatt. The readings seemed physically impossible. Robert Watson Watt, father of British radar, was summoned. He was a man who mistrusted miracles. The cavity magnetron was the kind of miracle he disliked most, one that contradicted established doctrine. How could a device with no control grids maintain stable oscillations? How could drilled holes in copper outperform decades of careful valve engineering? Randall explained the self-bunching mechanism and the cavity resonance that locked the frequency with remarkable stability. Watson Watt listened, skeptical but impressed. Then he asked the critical question, could it survive war? Could it withstand vibration, freezing temperatures, desert heat, and combat conditions? Tests suggested it could. The solid copper construction had no fragile grids or delicate internal structures. Boot admitted he had accidentally dropped the prototype and it still worked after minor retuning. That was enough for Watson Watt. 6 units were ordered for field trials. The Air Ministry, however, hesitated. Henry Tizard, Britain's most respected scientific administrator, feared investing in an unproven laboratory curiosity. Britain already produced meter-wave airborne radar systems and training crews to use them. Replacing everything mid-war carried serious risk. But every test of the magnetron produced results too extraordinary to ignore. By May 1940, experimental 10-centimeter radar sets fitted to test aircraft achieved detection ranges of over 4 miles, twice that of existing systems, and with tiny aerials that created almost no drag. The Magnetron was reliable, sturdy, and astonishingly powerful. Tizard approved it. Then he made a decision that would alter world history. On August 29, 1940, Tizard stood over a metal trunk containing Britain's most valuable secrets: the cavity magnetron, a working 10-centimeter radar set, proximity fuse research, jet engine blueprints, and nuclear physics documents. He intended to give all of it to the Americans. Churchill himself approved the risk. If Britain fell, these technologies would die with it. Better to share them with a future ally. Tizard and a team of elite scientists flew to Canada, then traveled to Washington, where American officials, deeply skeptical of Britain's chances, listened politely. That politeness evaporated the moment Bowen demonstrated the magnetron. When it boiled a cup of water placed in the beam, American scientists realized they were witnessing the most powerful microwave source ever built. Overnight, American industry mobilized. Bell Labs, General Electric, Westinghouse, RCA, all demanded technical briefings. An agreement was forged. Britain would share everything, America would commit its massive industrial power to production, and both nations would exchange every future improvement freely. Thus the MIT Radiation Laboratory was born, an institution that would employ thousands and consume billions developing microwave radar. Randall and Boot's copper block was about to reshape Allied warfare. Production challenges followed swiftly. Early magnetrons failed after 50 hours. American engineers solved this with improved cathodes and vacuum sealing techniques. By 1941, factories produced hundreds per week. By 1942, thousands. Magnetron output became the critical bottleneck of Allied radar deployment. Night fighter radars, maritime patrol sets, bomber navigation aids, all depended on this miraculous device. As mass production accelerated, the magnetron began arriving in British squadrons, and the war itself began to change. Over the blacked-out fields of Kent, Squadron leader John Cunningham flew a Beaufighter equipped with a new AI Mark 8 radar. Between his knees, a pale green glow swept the screen. His radar operator tracked a contact 4 miles ahead. Cunningham banked gently. At 1 mile he still saw nothing. At half a mile, the faint silhouette of a Heinkel emerged against the stars. Cunningham fired. The bomber's wing tore away. The entire interception had taken 4 minutes. This was the revolution the magnetron created. Radar that once required massive tower arrays now fit inside a fighter's nose. The drag-laden aerials of earlier systems vanished. The Beaufighter became a deadly predator in total darkness. German bomber losses climbed catastrophically. To conceal the radar's existence, British authorities spread the myth that pilots like Cunningham had exceptional night vision from eating carrots. German intelligence believed it. The real reason Germany's night bombing campaign collapsed was the 10-centimeter magnetron. At sea, the transformation was just as dramatic. Coastal Command's liberators patrolled the gray Atlantic, where U-boats prowled beneath storm-tossed waves. Previously, submarines surfaced safely at night to recharge batteries and attack convoys. The older ASV Mark II radar struggled to detect them amidst waves. But ASV Mark III, powered by the magnetron, could see a conning tower 12 miles away in total darkness. Suddenly, U-boats were hunted relentlessly. They began reporting aircraft appearing from nowhere during the night. Admiral Donitz suspected radar but rejected the possibility of 10-centimeter operation. German scientists insisted it was impossible. They were wrong. By mid-1942, U-boat losses surged, forcing them to remain submerged and slow. The Battle of the Atlantic began turning in the Allies' favor because the magnetron made the ocean transparent. By 1944, magnetron-based radar filled Allied aircraft. H-2S radar allowed bombers to navigate and strike through complete cloud cover. Pathfinder aircraft marked targets invisible to the naked eye. Night fighter radars like AI Mark X and SCR-720 gave Britain and America absolute nocturnal air superiority. Maritime aircraft hunted E-boats threatening the upcoming invasion. And when Operation Overlord began, this radar shield ensured the vast amphibious fleet remained protected from German air attack. 19 German bombers were shot down on D-Day night alone, crippling Luftwaffe response. The success of the Normandy landings, in poor weather, with thousands of aircraft operating simultaneously, owed much to the Magnetron's unseen vigilance. The device invented in desperation 4 years earlier had become an invisible guardian over Europe's largest military operation. And after the war, the Magnetron began an unexpected second life. In 1945, Percy Spencer at Raytheon noticed a chocolate bar melting in his pocket while he worked near an active magnetron. Within months, the first microwave oven emerged, a massive commercial unit called the radar range. Soon magnetrons powered civilian radar, weather forecasting systems, air traffic control networks, maritime navigation, medical diathermy devices, cancer treatment systems, and scientific instruments used in astronomy and physics. Microwave relay stations began replacing long-distance telephone cables. The world's first high-capacity communication networks were born from technology invented to see enemy aircraft at night. The price of a magnetron plummeted as millions were manufactured. What once was Britain's jealously guarded secret became a foundation of modern life. Today, every microwave oven, satellite link, Wi-Fi router, and long-distance communication system carries the legacy of Randall and Boot's copper block carved in a Birmingham workshop. The magnetron story is a reminder that the greatest breakthroughs often emerge during moments of existential crisis, created by people who do not yet know what cannot be done. It was designed to save Britain, but it ended up shaping the entire modern world. A device built to find bombers in the night became the heartbeat of the technological age, proving that even in war's darkest hours, human ingenuity can produce inventions whose light never fades.